Session 4 of Unit 1. In this session, you would be introduced to the structure of the atom and how it is involved in nuclear reactions. By the end of this session, you should be able to understand how the discovery of the various models of the atoms was done. You should be able to explain the fine structure of atomic lines. Let us look at the structure of atoms. There are several scientists that work to explain the structure of the atom, and the first among them was J.J. Thomson, and his model is what is referred to as Thomson's Plum-Bardeen atom. In the early 1900s, J.J. Thomson proposed one of the first models of the atom. He considered the atom to be spherical in shape, and the mass of this atom is evenly distributed across this spherical shaped atom. Also, the charges, he said, are evenly distributed across the spherical shaped atom. He also said that there are electrons that are embedded in these spherical shaped atoms like plums in a bardeen. Now, the plums in the bardeen is a traditional English dessert, a food, where it is made up of the sponge, something that looks like a modern day cake, and there are raisins that are spread out in the cake. So the electrons, according to Thomson, are likened to the raisins which are spread in the bardeen. So you can look at the diagram below. You realize that there are electrons that are all embedded in the atom. According to Thomson, with the electrons being embedded in the atom, there will be emission of electromagnetic radiations if any external force causes these electrons to vibrate. The search to better the understanding of the atom continued, and one scientist by name Ernest Rutherford put two of his students on a research to investigate the structure of the atom as proposed by J.J. Thomson. In an experiment, they bombarded fast-moving alpha particles on a thin gold foil. He observed the deflection of the alpha particles with the help of a screen. Now, according to J.J. Thomson's atomic model, an atom consists of a positive charged sphere. So the sphere is positive charge with electrons embedded in it. So it was Rutherford's idea that if the atom is of positively charged, then when the alpha particles, which are also positively charged, are incident on the atom, then there should be some massive deflections, and the species that are involved, the alpha particles should also travel through the atom. But when he carried out the experiment, he observed something that is contradictory to J.J. Thomson's model, where a major fraction of the alpha particles bombarded towards the gold sheet passed through the sheet without any deflections. Some of the alpha particles were also deflected by the gold sheet by very small angles, and some of the alpha particles were also deflected back nearly 180 degrees by angle. Now, because most of the alpha particles went through the thin gold foil without any deflection, J.J. Thomson concluded that, or deduced that, the atom is made up of open space. That's most of the space of the atom is empty. Also, because some of the alpha particles were deflected by small angles, Thomson concluded that the positive charge of the atom is not uniformly distributed. He also make another deduction that because very few of the alpha particles were deflected back, it means that the positive charge particles in the atom is very small as compared to the entire volume of the atom. Based on Rutherford's observations and deductions, Rutherford concluded that the atoms are positively charged, and that positive charge is concentrated at the center of the atom, and Rutherford named it the nucleus, and also said that there are negative electrons which are situated in remote points around the atom. Despite the important observations made by Rutherford, which gave better explanation to the structure of the atom, there were two unsatisfactory aspects of Rutherford's proposed atomic structure. One of them is concerned with how electrons are held in place outside the nucleus. Now, the idea of small solar system with the electrons orbiting the positive charged nucleus seemed attractive, but this was unaccepted to classical theory. According to such accepted theory, orbiting electrons experience a radial acceleration and should emit radiations. In doing so, they would lose their kinetic energy and spiral into the nucleus. But according to Rutherford, these electrons orbit around the nucleus without losing their kinetic energies and falling back into the nucleus. Another inconsistency was to do with how protons can be held together in view of the strong repulsive force of the positive charged particles. As such, Rutherford's ideas were indeed inconcilable with the classical theory of electromagnetism. And so, another scientist by name Bohr did further research in 1913. Bohr developed a model based on the new quantum theory proposed by Planck for radiation. Bohr proposed that the electrons orbit around the nucleus at certain fixed radii. We shall explain as we go on. Let us look at the Bohr's model of the atom in details. Rutherford's atomic model was quite commendable when it comes to explaining the structure of the atom. However, it was not appropriate theoretically. We know that any charged object revolving in a circular motion will gain acceleration gradually, and similarly, if the electrons are moving around the nucleus and are moving in a circular pattern, then they will gain acceleration gradually, and on gaining acceleration, they are bound to liberate energy. If they continue to radiate these energies, then at a point they will lose all their energy and fall into the nucleus. This will make the atoms highly unstable, but that is not what is observed. Naturally, all the atoms are stable, and so there should be modifications to Thomson's and Rutherford's model. So Bohr made certain postulates to further explain the Rutherford's model. He says that only certain special orbitals called discrete orbitals are allowed inside the atom, which means that even though the electrons are found around the nucleus, they are found at specific positions in the nucleus. And he also said, while revolving in the discrete energy levels, the electrons do not emit radiations. So the electrons, as they move in that specific energy level, they do not emit radiations. And he also said that radiations are only emitted when electrons move from one energy level to another. And this idea helps to better explain why the atoms are stable, because the electrons are not emitting radiation as they move around the nucleus, so they won't lose their energies and fall into the nucleus. There were other scientists that were doing researches, and they are finding spectra emitted by these atoms, and it is expected that since the electrons are moving around and they are losing energy, they should give spectra that is fine, like the electromagnetic spectra. But this spectra that is observed from the electrons are discrete and they are separated from each other. So Bohr used his model to explain this spectra. He explains that the electrons in the atom are quantized. That is, they are found within specific energy levels, and they can be found in between energy levels. So they either jump from one energy level to another energy level, and by so doing, they give off energy, and as they give off energy, they emit radiation. So these radiations are the ones that are seen as spectra. The next question we ask ourselves is, so what exactly are these discrete energy levels where electrons are found? We shall look at this next. The diagram is the representation of Bohr's model of the atom. In blue is a representation of the shells, that is the energy levels, and in the center is the nucleus with protons and neutrons in them. The blue and the red and the green colors are the elliptical representation of the energy levels. Now, to explain where exactly the electrons can be found within the atom and the number of electrons that can be found within the atom, there are four quantum numbers that Bohr used to explain. The first one is the n, the small letter n, which represents the principal quantum number, and it could be represented by the alphabets K, L, M, and N, starting from the shell that is closest to the nucleus. Also, the azimuthal quantum number, which talks about the subshells within the energy levels. So within the energy levels, there are other shells that can be found within the energy levels, and they are represented by L. We also have the Mi, which is the magnetic quantum number, which further talks about degenerate orbitals within the subshells. And then the Ms, which is the spin quantum number, and it talks about the axis about which the electrons can rotate. let us look at the four quantum numbers in detail. We begin by the principal quantum number, n. The n represents the main energy level of the atom, and it could be represented by letters K, L, M, N, O, and so on and so forth, and could also be represented by numbers where they are numbered 1, 2, 3 to infinity. Out of these principal shells, we can get subshells, which we termed as the azimuthal quantum numbers. So the numbers that are used to represent the subshells are referred to as the azimuthal quantum numbers, and it is represented by the letter L. Now, if you have a shell, the principal quantum number, you can derive the number of subshells that will be in that energy level from it. So if your energy level is, let's say, 1, that is the K shell, we can find the number of sub energy levels or subshells that are present within that energy level, and we do that by finding integers from 0 to n minus 1. So if our n is 1, then the number of subshells will be n will be 0 and n minus 1, which is 1 minus 1, and that is also 0, so we just represent it with 0. In conclusion, if the principal quantum number is 1, then the number of subshells that are within that principal quantum number or energy level is 1, and it is represented by 0. If your principal quantum number is 2, the L shell, then the number of subshells that can be found within that energy level will range from 0 to n minus 1. N is 2, so from 0, then you have 1 minus 1, then 2 minus 1, and that will give us the value 0 and 1. These L values that we have gotten can be represented using letters. So if you have L value of 0, it is the s orbital. If the L value is 1, then it is the p orbital. If the L value is 2, d orbital. If the L value is 3, it is the f orbital. Now we have looked at the subshells. Out of these subshells are other orbitals which we call the degenerate orbitals, and they are represented by M1. So if you have an L value of 0, the number of degenerate orbitals that are found within that energy level is 1. If you have, it's only 1, and it is represented as 0. Now the MLs also take values ranging from negative L to positive L. So if the value is 0, then it will take numbers ranging from negative 0 to positive 0, which is 0. If your L value is 1, then the number of degenerate orbitals will be ranging from negative 1 to positive 1, which will be negative 1 through 0 to 1, which means that there are 1, 2, 3 degenerate orbitals that can be found here. That is why when you have a p orbital, you have 3 degenerate orbitals in the p orbital, which are the px, py, and pz. Then the d orbital, which is L value of 2, will have 5 degenerate orbitals in it. Also, the direction in which the electrons are pointing can be represented by ms, and they take values from positive half to negative half. In addition to the protons, neutrons, and electrons that were found within the atom, there are several numbers of fundamental particles that has also been discovered and been hypothesized. These have been grouped into two classes: the leptons, which consist of electrons, muons, and neutrinos, and also the hadrons, which are the protons and neutrons. The hadrons are said to be composed of three simpler components, which are referred to as the quarks. The quarks are glued together by gluons and they carry strong nuclear force. These are self-assessment questions to help you